Okay guys, we're going to go ahead and do 10.3. Try the warm-up by yourself. This is a state ed question, and then put me on resume to see how you did with it. Okay, go ahead and hit pause, please. It says, using his ruler, Howell measured the sides of a rectangular prism to be 5 by 8 by 4. 5 by 8 by 4. The actual measurements, the computerized engineered measurements, are 5.3 by 8.2 by 4.1. Find the relative error in calculating the volume. Volume means to multiply it out, so it's 5 times 8 times 4. So Howell came up with a volume of 160 cubic centimeters, whereas the actual, if you multiply 5.3 times 8.2 times 4.1, you would come up with an actual of 178.186 cubic centimeters. If they want you to find the relative error, which we've done quite a few months ago, relative error is equal to, you find the difference between the two. I'm going to go ahead and put the larger one first. The book always uses absolute value, but if you put the larger one first, you won't have to worry about that. And always divide it by the actual. So when you subtract the 178.186 minus the 160 that Howell got, and then take that 18.186 and divide it by 178.186, you're going to end up with 0.10206.189. It keeps going. They want us to round it to the nearest thousandth. So therefore we're going to say about 0.1000th is the 10th hundred is the third place value. So it's 102. And that would be equivalent to, if in case they asked for a percent, you would loop it over two places, it would be about 10.2%, which is a pretty significant relative error, which means really, to be putting it precisely, Howell didn't measure very well. Okay? All right, we're going to do 10.3, which is operations with radical expressions. You can only add or subtract like radicals. So understand, add and subtract, they have to be like. Okay, when you multiply and divide, you don't have to have like. That's why it's actually easier to multiply or divide. Be careful though. Some expressions may be deceiving if their radicands are different. Make sure you fully simplify the radicands to see if they are like. Don't look at them and think, oh, well, because they're different radicands, they can't be like. They may have to be simplified first. If you look at the first two examples, which are very basic and easy, notice that the radicands are already the same, root 2 and root 2. So you go ahead and subtract 7 root 2 minus 8 root 2 would be negative 1, which I'm going to leave as imaginary, root 2. So notice that when you add and subtract, you only add and subtract the coefficients. The radicands stay the same, just like when you do with variables. In the second one, we have 5 root 5 plus 2 root 5, that is 7, and root 5 doesn't change. Okay, these two questions were set up easy because the radicands were already like or easily seem to be like. Let's look at some that are not. So if we look at these two questions, let's start with the first one. This is not supposed to be here, so please ignore the little, when I snapshotted it, it didn't come out as well. We have 4 root 7 plus 2 root 28. Some kids are going to look at this and say, these guys are not like, so I can't add them. However, 28, the radicand 28 can be simplified. So you have to simplify first before you make that decision. The square root of 28 can be broken down to a perfect square of 4 and then times 7. The square root of 4 comes out as a 2. And then we're going to multiply that out by the leading coefficient. 4 square root of 7 is fully simplified, plus 2 times 2 is 4 square root of 7. Notice now that your radicals are the same. If your radicals are the same, then they are like radicals. As a matter of fact, the indexes have to be the same too, but we're only dealing with square roots. There's a little imaginary 2 here and a little imaginary 2 here because it's a square root. If nothing's there, you know it's a 2. So 4 root 7 plus 4 root 7 is 8 root 7, fully simplified. Look at the next one. 5 root 32 minus 4 root 18. Let's simplify our radicands. 32 can be broken down. If you pick the largest perfect square, it's 16 times 2. If you pick 4 times 8, you'll have to simplify it again, which is totally okay to do. The more you do these, the quicker you'll get with finding the perfect squares. Square root of 16 is 4. Square root of 9 is 3. Multiply that out by the leading coefficient. 4 times 5 is 20. Root 20, or excuse me, root 2 minus 12 root 2. They are like radicands. They have the same radicand and same index of 2. 20 root 2 minus 12 root 2 is 8 root 2. When multiplying radicals, you do not need like radicands. That's why it's a little bit easier. Only when you add and subtract do they have to be like. So if we look at these examples, these are seen on the state exam a lot, so let's be careful. In the first one, we have to actually do the distributive property. What you want to remember when you're multiplying or dividing, it's always coefficient by coefficient, radicand by radicand. So I have 1 root 2 times 1 root 6 is 1 root 12. Plus 1 root 2 times 5 root 1 would be 5 root 2. They don't put the imaginary ones in there. Now the square root of 12 can be simplified to 4 times 3 is 12. Square root of 2 is already simplified. Square root of 4 is 2. 2 times 1 is 2 root 3 plus 5 root 2. Notice that my radicand 3 is different than the radicand 2, so I cannot add those together. That's the simplest form. The next problem sneaks up on a lot of kids. You see the squared? We've seen problems like this before. You cannot use the power rule because this is a binomial. You have to use FOIL. So rewrite it out and don't get tripped on this one. FOIL it. First, outer, inner, last. Root 11 times root 11 is root 121. Outers is root 11 times negative 2 is negative root negative 2 root 11. Inners is negative 2 root 11. And last is positive 4. Let's go ahead and simplify some stuff up here. We know that the square root of 121 comes out as 11. So that's going to give us 11 minus 2 root 11, negative 2 root 11 and negative 2 root 11 are like terms. So negative 2 root 11 minus 2 root 11 is minus 4 root 11. Plus 4 drops down. We have like terms again. 11 and positive 4 comes out to 15 minus 4 root 11. Can't subtract those because they don't have like radicands. Okay, so be careful with this. This is tricky. I've seen that on the state exam quite a bit. This one's going to be a little bit longer. Hopefully I have enough room here. FOIL. First would be 1 root 6 times 4 root 3 would be 4 root 18. Outers would be root 6 times 3 root 6 would be 3 root 36. Inners is negative 8 root 9. Last is negative 6 root 18. So let's simplify what we can here. Perfect squares, that'd be 6, that would be 3. And 4 root 18 is a like term with negative 6 root 18. So those guys combine to negative 2 root 18. And we got 6 times 3 is 18. And 3 times negative 8 is negative 24. Alright, we got negative 2 root 18. 18 minus 24 is negative 6. Square root of 18 breaks down to 9 times 2. 3 times negative 2 is negative 6 root 2 minus 6. That was a tricky one, so be careful. If you need to replay it or try it by yourself, please do. Alright, this is tough because, and this is an honors level question, rationalize the denominator when it's a binomial. Anytime it's a binomial with a radical in it, you're going to have to use the conjugate, which means change the operation and multiply both numerator and denominator. Okay, so let's look at this. If I have negative 3, you guys have had radicals in the denominator before. The only difference now with this problem is that it's not a monomial. This is a binomial. This is very different than what you guys did before, so pay attention. You're going to multiply by what we call the conjugate. Now, the conjugate is still going to represent a fraction that is 1. The difference is you're going to multiply by the conjugate of root 10 plus root 5, which is root 10 minus root 5. So it's the same binomial. The only difference is you change whatever the sign is to the opposite. Make sure you do it to both numerator and denominator. Okay? Now, this is going to be quite a bit of work because you have to do the distributive property up here and FOIL down here. Negative root 3 times 10 is negative 3 root 10 plus 3 negative times a negative, so we get 3 root 5. Okay, here we go with FOIL. First, root 10 times root 10, root 100. Outers, root 10 times negative root 5, root 50. Inners, root 5 times root 10, root 50. Last, root 5 times negative root 5, negative root 25. Now, what you should notice, when you multiply by the conjugate, it's going to get rid of all the radicals. These guys cancel each other. The square root of 100 is 10. The square root of 25 is 5. So up in the numerator, you can't add these because they're not like, so we end up with negative 3 root 10 plus 3 root 5 all over 10 minus 5, which is 5. And there's nothing else I can do, so I'm done. Okay, let's try this one. This will be the last question since I am running out of time. Notice one of the things you should be able to pick up on is it's a proportion. So let's go ahead and cross multiply. 4 times 2 is 8. And we got to multiply the W times the 1 plus root 5. Don't do distributive property on this because we're solving for W, which means really divide by 1 root 5. That will cancel here and here. So W is equal to 8 divided by 1 root 5. Well, that's great, but you can't leave a radical in it. So you're going to have to multiply by the conjugate since it's a binomial, which would be 1 minus root 5. Same binomials, change the sign, and do distributive property. And then do FOIL, which will actually cancel all of your radicals. First, outer, inner, last. So we end up with, these guys cancel each other, and the square root of 25 is 5. We end up with 8 minus 8 root 5 all over 1 minus 5, which is negative 4. All the coefficients can be divided out by 4. You divide that by 4, let's do negative 4. Negative 4, negative 4, so we end up with negative 2 plus 2 root 5. That was tricky. I'm almost out of time here, but please actually try this again by yourself and then have me replay it. Okay?